So we are going to continue the discussion on the jet engines. The discussion today is going to focus on the turbofan engines, and we are the first part of the turbofan engines which we are going to discuss today is a small is a short lecture actually. It's a small part of the bigger discussion we're gonna have on Wednesday and later on after Wednesday. So what we are going to do is we're going to go over the equations, the concepts, and all the things. Then we will do the same thing we did on Wednesday. I will give you one of the examples. I will ask you to solve it, and if you do so, you will need to do the quiz, right? This week. I think it's a good plan because it's going to help you guys a little more, but I will be a little more active before compared to the last one. So turbofans, essentially a combination of fans and a jet engine, right?
Well, the buzzing happened to wildfire. Oh, I heard enough.
Really?
It really distracted me.
Okay, it is distracting.
But what it sounded like, it just sounded like a faint humming on the recording.
Okay. So the thing about the turbofan engines, as you can, this is a turbofan engine. We actually have one additional station here, and you have to be aware of that, and that's the station 19, which is the fan exhaust. But not all of the turbofans look like this. We will talk about them shortly. But the multiple loadings, because of the presence of the fan, is going to require us to have different turbine stages, which are referred to as spools. So we essentially, what it means is that we're going to have low pressure turbine, high pressure turbine, which means that we're going to have the same things for the compressor as well, right? And these two shafts, they're going to rotate beside each other, but one of them will be, if you have a two-spool turbine, you're going to have two shafts that are rotating. One of them is the inside of another one. They are rotating at different speeds of N1 and N2, and they are going to serve two different purposes. One of them is going to serve essentially provide the energy for the fan blades rotation, and the other one is going to provide the energy for the compressor part of your turbojet engine. Okay, but we have two main parameters in a turbofan engine that are not present in a regular jet engine. The first one is the bypass ratio, which is the ratio of the flow rate in the fan bypass duct to that of the gas generation. So the ratio that's going, the ratio of the bypass divided by the ratio end of the core. Okay. So does this make sense, or is it clear?
Yes.
Whatever going in here divided by whatever going in here. And the other parameter is the fan pressure ratio, which is the ratio of the total pressure of the fan exit to that of the fan inlet. This specific type of turbofan engine is called the separate exhaust turbofan engine, which essentially it is very self-explanatory, right? Essentially, it means that the exhaust of the turbojet engine or the core of the engine is going to be separated from the exhaust of the fan. This separate exhaust makes the calculations much simpler, makes the analysis much simpler, but doesn't give you doesn't. Let's just say it will make your calculations much simpler, but it doesn't mean that we don't have any other type of turbofans. There's another type of turbofans which is the mixed. It's called the mixed exhaust turbofan, and you can see on the right here. The main difference here is that the fan exhaust is going to be mixed with whatever that is coming out of turbine. Okay, so essentially, if you have this type of engines, your mixture, the mixture part, which is usually called by the station 6M, is going to happen before the afterburner, if you have any afterburner, right? So that mixing is going to happen after the afterburner. Which this topic is going to be the mixed exhaust fans, turbofans is going to be the topic of the next lecture, and probably the next lecture on Monday. It's a little more complicated compared to the regular turbofans, and both mathematically and theoretically, right? But in some cases, it gives you higher efficiencies, and we will talk about all of those things later. Okay. Is there any questions so far? Yes.
So the second one is bypass, but
yes.
Mixes at station 6.
Exactly. So this is going to be your bypass, right? And then mix here. Right? This is going to be your core, and whatever coming into the core is going to be a dot notch, right? Whatever going around the core is going to be your fan mass flow rates. But then the question is, let's focus on the separate exhaust turbofans, and let's try to analyze it. The first question you want to answer is that how do we treat the thermodynamics of this type of fan? Without looking at the HS diagram, let's think about this first. How do we treat the thermodynamics of a fan? How should we answer this type of question? The first thing you want to do is to think of what is the job of this fan, essentially.
Provides work. Provides work.
Provides work. Okay. What is the job of the fan here? What does it do to the air? Speeds up the air. Speeds up the air. Okay. So, okay, let's go around it. Okay. So we have one adds work, one speeds up the air and adds momentum to the air. What else? Let's go with Anna Victoria here.
I don't know what else. I thought it adds momentum.
Okay. I'm not saying it's wrong. I'm just getting it.
Yeah, I mean, they're both essentially the same thing. You're adding velocity to the air, adding momentum to the air, you're adding work to the air. Like,
the fan also compresses the air a little bit.
Okay. So the fan, Nimlab is telling us the fan is going to compress the air, which does compressing the air contradict adding momentum to the air? Yes or no? You have pressure time in your momentum equation as well, right? Yes?
They're related to each other.
They are related to each other. So it doesn't necessarily contradict each other. So we had one increase in velocity, like two other momentum increase, and one increase in pressure. Let's say you are all correct, right, from your different perspective. Based on what you are thinking of what a fan does, how can we analyze it? Or what is it more similar to in an engine, inside an engine core? Is it more similar to the inlet nozzle, the inlet diffuser, the exhaust nozzle, or turbine, compressor, burner? I don't think it's similar to burner at all, right?
Inlet nozzle.
Inlet diffuser, right? Inlet diffuser. Okay, what else?
I would say it's similar to the exhaust option here. It's like what provides the thrust that increases the speed.
But your CP doesn't change. Like the nozzle has a different CP from the inlet.
Yeah, that's
You could count coming into the fan as like inlet. You could count exiting the fan as an exhaust nozzle. If you go from the front. Depends if you're counting, if you're trying to do the equations for entering the fan or exiting the fan. That's what I'm trying to say.
so you are saying it's not just one stage, the fan. It's
The
like
fan,
a couple of
well,
stages.
the fan is one stage, but if you, the way that I was thinking about it is like you do the equations for the front of it, then you do the equations again. I guess it's closer to a nozzle than that.
But we never do an equation for one surface. We do an equation for a control volume, right? So inlet and exhaust, right?
Like, I know it's not like a combustor, but you can think of the fan as like the gas generator. That's you have the inlet, and it goes through the fan, and then accelerates the inlet.
Okay.
I think the compressor, because when the fan takes in the air, isn't the air afterwards heated up and mixed with gasoline? Or is that
In a turbofan, no. There's no combustion in a turbofan. Huh?
Oh, that's the turbo.
There is a combustion inside the core of a turbofan, but there's no combustion in the fan, right? It's just takes the air in and gives it out.
You were talking about afterburns, so I thought.
No, that's for a mixed exhaust. We are not doing mixed exhaust here. We are doing separate exhaust. So we are working on this one. Okay, the one on the left. So, but you are correct. It is treated the same way as you treat a compressor in the analogy. So what does it mean? Like we had all of this discussion, what does it mean? Actually, it becomes a little clearer when you look at this HS diagram. Especially, it is the same way. It is treated the same as a compressor when you are trying to calculate its efficiency, right? Which is mostly what we do here. We calculate the efficiency, or we use the efficiency to calculate something else. So, how did we treat the efficiency of a compressor? How did we find the efficiency of a compressor? No, what was the definition of the efficiency of a compressor?
Total efficiency, that's propulsive times the thermal.
Efficiency of a compressor. So thermal efficiency was for jet engine, right?
Yeah, deal over the actual.
The ideal over the actual, right? Is this what?
I was gonna say isotopic over actual.
That's the same thing, right? So the ideal power that a compressor needs to compress the air divided by the actual power it uses to compress the air, which is always higher than your ideal power. The same thing is going to happen in a fan, right? The ideal power your fan needs to compress the air inside the fan is going to be always lower than the actual power the fan is going to need or use, right? So the ideal power is, of course, when you go from station 2, which is the inlet of the engine, to the station 13, which is the exhaust of the fan, isentropically. And the actual power is that what is essentially what really happens. So the enthalpy difference when you go from a station 2 to a station 13 isentropically is going to be on the numerator divided by the enthalpy difference of the actual case. Okay. Is this clear? Yeah. Okay. So what you can do to simplify this is to divide the, use the definition of the enthalpy, which was CPDT or CPT. And the CPs are not going to change in the fan, but there is no burning, there is no adding fuel, there is no nothing, so we can safely assume that the CP at the exhaust and the inlet are pretty similar to each other. So, and you divide everything by the TT2, your equation is going to become TT13S, the isentropy divided by TT2 minus 1 over TT13 divided by T2 minus 1. Okay. Well, what is this? This T13 over TT2, that's your temperature ratio of the fan. That's how we define the temperature ratio, right? So we're going to have tau of F here, and this one is going to be the isentropic temperature ratio of the fan, right? Or the temperature ratio of the fan when the process happens isentropically, right? So we can use the isentropic relationship and replace that with the pressure ratio of the fan, right? So your fan efficiency is going to be pi of F to the power of gamma minus 1 divided by gamma minus 1 over tau of F minus 1. So we can rewrite this whole thing to give us the temperature ratio or the pressure ratio, which is essentially what you usually do. You usually get one of the temperature, the pressures get, and you have to calculate the other one, right? So we can essentially rearrange the equation a little bit to give us tau of F, same equation, just a rearrangement of it, and we can do the same thing to get the pi of F. Is there any questions? Okay, so let's move on. The idea was that your turbine this time has to provide energy to the compressor as well as a fan, right? So your energy balance of the whole system is going to be a little bit different this time, right? Because you have the fan and the turbine and the compressor both, right? But before writing the energy balance, let's make sure we are consistent with the terminology and we understand the terminology here. And that air coming in is going to be equal to whatever going inside this core, the core of the thing, plus the bypass ratio, right? The bypass air, right? The bypass air is going to be equal to bypass ratio, which is alpha multiplied by m dot naught, which is m dot, the mass flow of the core, right? So your total m dot air that is going into the engine, not just the core or the fan, is going to be 1 plus alpha multiplied by m dot naught, or m dot naught plus alpha m dot naught, right? So we have just taken the m dot naught out. And we are also adding fuel at the burner, so your jet exhaust mass flow rate is going to be m dot naught plus m dot f, which is 1 plus f m dot naught. Okay. So let's write the energy balance for this system. What is the total? Well, let's try to write this. What is the total energy produced in this turbine, in this engine? The total energy produced by the turbine, right? The mechanical energy is produced by the turbine, and we are talking about that mechanical energy balance.
So
that goes
the compressor power and the fan power.
Can you repeat that?
So you're asking like how much power is produced by the turbine?
By the turbine. Go ahead.
No, I remember like before we were saying that the turbine power is always equal to the compressor power times an efficiency factor.
Okay, so, but we, yeah, okay, so what is added here?
The fan.
The fan, okay, so the turbine power is equal to the compressor power plus the fan power, right? That should be the conservation of energy, right? But how can we calculate the turbine power by itself? The enthalpy difference between the inlet and exhaust of the turbine, right? That's it. We do the same thing for all of the stations. And that we, if you recall, we defined this mechanical efficiency, right? Eta M, which was the energy loss in the gearbox and all of those things that may be there, that will definitely be there, right? So the total power produced, energy produced inside the turbine is going to be your mechanical efficiency multiplied by the m dot naught, which is the core m dot, engine core m dot, multiplied by 1 plus F, because we also have the fuel there as well. And the enthalpy, the total enthalpy difference between the exhaust and the inlet of the turbine, then that is going to be equal to whatever that is going to the compressor, which is your m dot air, m dot naught, the engine flow rate multiplied by HT3 minus HT2, plus the fan part, which is your bypass ratio multiplied by m dot naught, multiplied by HT13 minus HT2. Okay. Is there any questions here? I think it should be clear, right? And we have done this simplification before for the energy balance where we only had the compressor. I think we went over it, that how these temperature ratios all pop up. But you can go over it again and do the rearrangement and do the simplifications yourself to get to this equation. So your energy balance is essentially going to be the enthalpy ratio compared to the ambient enthalpy ratio of the turbine exhaust compared to the ambient enthalpy and the temperature ratios and all of those things. The fan temperature ratio, compressor temperature ratio. Which means that we can replace it with replace everything. So let me actually, before going for, just to make sure that you remember. What was this ratio? What did we call this ratio? That's the enthalpy at the exhaust of the turbine divided by the tau lambda. What about this one? Tau R, right? A lot of parameters, so I just wanted to make sure that you are clear. So we can plug those in, tau R and tau lambda, and find a turbine temperature ratio, which is essentially going to be telling you the expansion you are going to need to get out of the turbine, right? As a function of the compressor properties and the fan properties, as well as your fuel to air ratio. So this equation is going to let you know how much expansion you're going to need to have inside the turbine when you include a fan in your system. Does it make sense? Okay. Well, how can we calculate, or what kind of a change will we see in the fuel to air ratio? Is it going to change at all or not? Not really. Why not? Because the compressor or the combustor is at the stage where you haven't seen, the engine core hasn't seen the effects of the presence of the fan around it yet, right? so that we can use the previous equations we have had for the regular turbojet engine to find the F, which is of course a function of T lambda, TR, TC, and the heating value and the efficiency of the burner, all of those things. We have seen this equation many times before, like a couple of times before. So if you have that F, if you have the temperature ratio HT2 or H0, if you have the compressor temperature ratio, fan temperature ratio, bypass ratio, you should be able to get the tau of T. Okay. So let's take a look at this equation again. It's the same equation, right? We have just tried to separate the two parts of it. One part is only the contribution of compressor. So the expansion you need in a turbine to drive the compressor, right? And the other part is going to give you the expansion you need, the expansion you need in the turbine to be able to drive the fan, okay, the turbofan, right? The fan part of the bypass part of your engine. So is there any way this temperature ratio become negative? Is there any way for this temperature ratio to become negative? Okay, how?
So the temperature ratio become negative, right?
I'm not talking about the physical. Of course, in reality, this temperature ratio cannot be negative, right? That's for sure. I'm just talking about the mathematics of it.
The inlet and the nozzle get switched.
The inlet and no. What do you mean by that? The inlet and okay. No. So mathematically, for this tau of T to become negative, you have to get a negative value from here. Which means that you have to have two negative values that combine to each other is going to give you more than one. Right? My question is that possible mathematically? Is it possible for it? Is it possible to happen? Is it something like that possible?
Horrible mechanical efficiency.
Horrible. No, that doesn't usually happen, right? Actually, there should be a little physical reality to it. Let's look at the numerator. The tau C is your compressor temperature ratio. What do you expect to see there? Do you expect to see tau C larger than 1 or smaller than 1? Larger than 1. Okay. But is it going to be close to 1 or not? Go back to the example you saw for the previous lecture. What did you see after the compressor? How big of a temperature change did you see?
It's a good engine, it'd be a good one.
Yeah, it was like double.
Okay, double. So your temperature ratio was essentially 2. Okay. What about TR?
One. Later.
That's all right.
That was like 2.
2. Okay. So we can go to each of them one by one. But eventually, what you're going to see is that this term is going to be pretty small. Often. The main contribution, when you have a turbofan, the main contribution comes from this term, right? And there's one element in this term that actually can become 30, 40, right? That there's one ratio that can be achieved, and there are some designs that have those type of ratios, right?
So the bypass ratio high?
Yeah, the bypass ratio, yeah. So there's this, the bypass ratio can be 30, 40, but when that happens, not when that happens, but that can also means that your temperature ratio can be, the fan temperature ratio can also be so big, right? So what's going to happen there when you have that bypass ratio and you have that huge temperature ratio, right? You're going to have a negative number. Does that make sense? No, right? Because why? You can't have negative temperatures, right? We are talking about absolute temperatures. There is no way you can have negative temperature, right? It doesn't really matter how much of a small or large negative temperature ratio you have. You cannot have, right? So what does this tell you? When based on this equation, you may end up having a negative temperature ratio outside of the turbine. What does this tell you? Just think about it. Let's say the fan, the bypass ratio of the fan, or the temperature ratio of the fan is so big that is going to give us a negative temperature ratio in your calculations, of course, right?
So the numerator would have to be the larger value.
What will it happen? What will it mean for your design? Right? What does it mean? What is it? Where is the deficiency? There is some deficiency somewhere, right? There is a problem somewhere that you are getting that negative value of the turbine expansion, right?
So there's no air going to the core. It's all going to the bypass.
There is no air going to the core, all is going to the bypass. You're getting a little hot, so you're getting closer. Right? You won't get this value in a real world condition, right? Just like so think about it, you're in the design state and you're designing an engine that will give you the negative temperature ratio, right? You have to change some part of your design. That's of course not to get a negative temperature ratio. But let's say you end up designing it, right? You go ahead and do this because design. What does it mean? Yeah, like you create a map, you create a whatever in the SolidWorks CATIA and just send it to the shop. That's it, right? It doesn't have to work. Right? You can create it, right? But what does it mean? What does it mean for your design? It essentially means that the maximum expansion you are going to get out of your turbine is not going to give you enough power to rotate the fan. Pretty simple, right?
So just make the fan bigger.
Maybe make the fan small, right? Or make the turbine a little more powerful. Does it make sense? Okay. So which tells you that you have a limit as far as it comes to the expansion or the power you're going to deliver, you will be able to deliver to the fan, right? As we said, this part A of your system talks about the turbine expansion. Part B of your equation here talks about the turbine expansion. Part A, turbine expansion that supports the compressor. Part B, turbine expansion that supports both the compressor and, of course, the addition that supports both the compressor and the fan. And there is always a maximum. There is always a ceiling. you cannot go away from. So you have to make sure that you are, in your design, you stay within this range, right? You have the maximum range, you're going to get all of your compressor at the fan, and then you always stay within that range. And something that you have to keep in mind is that this graph has 1 minus tau of t on one of the on the axis, right? So we can compare that to the maximum bypass ratio of your system. Actually, we can have another graph, 1 minus tau of t and alpha of max, the alpha in general, the bypass ratio. What is that going to mean? Is that for a specific fan pressure ratio, you are going to be able to get, or you cannot go further than a maximum bypass, right? There will be a maximum you can get for a specific pressure ratio, fan pressure. Does that make sense? And as you increase that fan pressure ratio, your bypass ratio is going to become smaller and smaller. Okay, so we are familiar with the turbofans at this point, and we know how to calculate the efficiency. Let's calculate the thrust. What's going to happen to your thrust? You of course you're going to have additional terms in your thrust, and this is a separate exhaust. So we will have a contribution from the velocity. We will have a contribution from the pressure change. Right? The velocity contribution is going to be your exhaust contribution, your alpha and dot, which is going to be your fan or your bypass mass flow rate multiplied by the V9. V19. This should be V13. Why is this V19?
That's the end of
Yes, yeah, we have a station 19. Yeah. Okay, so yeah, right. So we have one contribution from the exhaust of the fan, and we have always had this contribution from the exhaust of the core, minus the total air coming in at the station 0, at the ambient, at the flight condition, right? So that's 1 plus alpha multiplied by m naught dot. And we always have the pressure contribution, P9 minus P naught multiplied by A9, and P19 minus P naught multiplied by A19. Okay, so this is how you calculate the uninstalled thrust, right? What about a specific thrust? What is going to change in the specific thrust calculation? What do you guys think? What was the definition of the specific thrust?
That just the uninstalled thrust divided by m dot naught. That it would be 1 plus alpha divided by
Okay. Well, what is going to alpha m dot naught is going to be only the fan.
I mean, they combine that.
1 plus alpha m dot, that's what the total m dot air. That's the, yeah, exactly. So it's going to be f of n divided by 1 plus alpha m dot naught. This means that the upcoming air mass flow rate, right? So you plug that in, you can do the simplifications to get to the equation. What's going to happen here if we are dealing with a perfectly expanded nozzle? What about a perfectly expanded nozzle in the fan? Okay, so that will go to 0 as well. So this your specific thrust is going to be like this. And TSFC, the specific fuel consumption, is going to be under F over F of N, which is equals to F divided by F of N, or F divided by your specific thrust. but something that you have to keep in mind is that this specific thrust here in the denominator is not the specific thrust you want to calculate for your turbofan engine. This only includes m dot f, right? Because m dot not. But m dot f doesn't have any relationship with the fan mass flow rate, right? It's just related to the core mass flow. So if you were to use this equation, or if you were to use this in your calculation, you have to be mindful of, let me, okay. Are you guys done writing? Okay. Okay. Is there any questions so far? No? Okay. So how can we calculate the thermal efficiency here of a turbofan engine? Let's go one by one again. Let's start from Joshua. It's getting a little bored. So don't go back. Just think about it. What was the definition of the thermal efficiency of the engine?
It's like kinetic energy over like fuel energy. So you would just add the terms from the fan to the kinetic energy.
That's it, right? The kinetic energy jump divided by the total heat input, right, of the system. So what is the kinetic energy jump when you include the fan? You're essentially going to have one extra stage, right? The V19 part, V19 squared divided by 2 multiplied by the m dot of the fan, which is alpha m dot, right? M dot not. So these two parts are your kinetic energy at the exhaust, and you have the kinetic energy at the inlet, divided by the total heating value, the total heat input that is there because of the fuel. So this is going to be your real thermal efficiency. But the ideal case of thermal efficiency is not going to be different than how you calculated the ideal thermal efficiency previously. If you recall, we had this equation for the thermal efficiency, the ideal thermal efficiency, which was related to your flight Mach number and the compressor pressure ratio, or the temperature ratios, the tau R and tau C, right? This is going to be the same, the ideal thermal efficiency. What will happen to us when our exhaust nozzles are not perfectly expanded and we don't have the pressures information? You can actually simplify your solutions by using an effective velocity, effective exhaust velocity, instead of the regular velocity, which essentially means that if you have the fan gross thrust, is divided by your mass flow rate of the fan, and if you have the core gross thrust, you divide it by the mass flow rate of the core, you get that effective velocity and use those in your calculations of thermal efficiency if your exhaust nozzles are not perfectly expanded.
What's the last one?
Okay. So the propulsive efficiency, if you recall, was the thrust power divided by the jump in the kinetic energy. The thrust power is your thrust multiplied by the V naught. So we have the thrust formula just multiplied by V naught. And then divided by the jump in the kinetic energy. The assumption here is that we don't have a perfectly expanded nozzle, so the jump in kinetic energy should be calculated by the effective velocities. But if you have the perfectly expanded nozzle, you can make the simplifications. Eventually get this propulsive efficiency from a turbofan engine and compare this equation we have here to the equation we have for the regular turbojet engine, right? For a perfectly expanded nozzle. Is there any questions? No? Okay, so that's it for the turbofan with a separate exhaust. It took us a little longer than I expected. But as I said in the beginning of the class, let's solve this example again together. The same as the previous example that we did on Wednesday. Or Wednesday, was it Monday or Wednesday? Wednesday, yeah. So if you stay in class, solve this, and show me your solution, you can submit this as the solution to this as a part of your quiz. And otherwise, you have to take the quiz. Right?
So what are we doing Wednesday?
Wednesday is going to be turbofans with mixed exhaust. And next week is going to be turboprops, and hopefully we'll be done with this chapter 4. With a small discussion on ramjets maybe. It's cold in here.
So is the plan still to go to UAVs, or because I know you said you may not change it?
Yeah, we'll probably do the UAVs, but I will see what happens. So, yeah. Let me actually